Am I audible?
Yes, sir. Yes.
Okay.
I'm making presentation.
So from where I can share my slide?
I'm making you presenter, sir. 1 minute, sir. Yes, sir. Now you are the presenter. You can share. First, I'll give us our introduction about you, sir. Then we'll start.
Okay.
So, dear participants, I welcome you once again to an exciting and technically sound session on the topic sketching and sampling techniques for big data by Dr. Rameshwar Pratap, sir. Dr. Pratap is assistant professor at School of Computing and Electrical Engineering, IIT Mandi, and he's a young and dynamic algorithmist whose research work focuses on developing dimensionality reduction algorithms. Dr. Pratap had completed MCA from JNU New Delhi and received PhD in theoretical computer science from Chennai Mathematical Institute in 2014. He has also been worked in industry research labs in areas of algorithms in data science and machine learning at Wipro AI Research Bangalore. He's also been associated with TCS Innovation Labs, New Delhi. He has also spent a few months at IIT Bangalore as a research associate. We are grateful for his presence among us. So, without further ado, I would like to please welcome Dr. Rameshwar Pratap to join us and share his expertise. So, before that, I would like to uh, request Professor S.K. Singh sir to introduce you, sir.
Good morning, Dr. Rameshwar Pratap.
Good morning, sir.
Good morning, good morning. So, thank you for accepting our invitation and giving us your valuable time for our this short-term course. So, I hope our participants will enjoy your lecture. So, yes, Dr. Pratap, thank you very much.
Okay. Thank you, sir, for your kind introduction.
Yeah. And in future also, we will take your help for conducting such short-term courses.
Sure. So,
okay.
Thank
you.
Yeah, I'll try to share my screen. So, is my screen visible?
Not right now, sir.
No, sir.
No, it's not.
Yes, sir.
Now is it visible, right?
Yes, sir.
Okay.
No, it's not visible
No.
to me.
It's not visible, sir.
It's not visible.
Okay, so let me share my.
So you can go to the browse option in the share tray. You can go to the browse option and then upload from my computer.
So is it visible now?
No, sir.
No.
Dr. Pratap, otherwise you can share it on our mail also. We will upload it here and you can take control.
Sorry, there is some glitch in my internet today. So
Okay, so you can share your PPT on the email with us, and then we can upload it.
okay, so I'm sharing it on the email ID coordinator stc.idapt @gmail.com.
Yeah, sure.
So I just emailed you the slide.
Okay, sir. Checking. I've got it, sir. I'm uploading it.
Okay.
Sir, you have sent a PDF file with us.
Yes, yes.
Actually, this is not supported by MS Team. If
Okay.
you are having a PPT or version of it,
Ankit, you can share the screen and then take control to sir
okay, sir.
without uploading it.
Hello,
Yes, yes.
sir. Is the screen visible now?
Now I can see the screen.
Okay, sir. Yes, sir. You can start and you can say next. I'll move it for you.
Okay. So thank you for inviting me and sorry for the delay due to internet problem. In today's talk, I will talk about my work on sketching and sampling algorithm for big data. So next slide, please. So yeah. Yeah, so this is outline slide. So first, I'll briefly talk about the algorithm for big data, its motivation, and some necessary background. And then there are basically two parts of the talk. In the first part, we talk about efficient sketching algorithm for discrete data set, in which there are two parts. We'll be focusing on this binary data set as well as categorical data set. And in the third part of the talk, I'll talk about sampling algorithm for big data set. Next. So in the areas of developing algorithm for big data, we need to develop algorithms that can handle large dimensionality and large volume of the data set. Next. So in high dimensional data set, in many real life applications, we have high dimensional data sets such as high dimensional text documents due to its large vocabulary, and high dimensional images due to large number of pixels in the images. Next. And the possible remedy to address this high dimensional data set is to perform dimensionality reduction or sketching. Next. So similarly, in many real life applications, we have a large volume of data set. For example, in the same examples, we have a large number of text documents, and we may have a large number of images. And since due to the number of data points are large, we cannot afford to run algorithms on these large number of data set. So the possible remedy to address the large volume of data set is to perform sampling. So basically, given a large volume of data set, we need to carefully sample points so that these sampled points maintain some nice inherent property of the original data set. So basically, we have high dimensional data sets, and we'll address those high dimensional data set due to sketching and sketching algorithms. And when we have large volume of data sets, we address the large volume of data set by sampling algorithms. Next. So standard practice for handling large volume and dimensionality of the data set is to develop efficient algorithms, or basically tools such as Hadoop and MapReduce. But next, but in sketching and sampling techniques, our approach is slightly orthogonal.
One minute, sir. I think we are facing some technical issues. We are working on it.
Is it visible now?
Yes, yes.
Yes, sir, it's visible.
Next. Yeah, so next slide, please. So
Sir, on which slide do you want? Hello. I think the speaker is facing some technical issue. We'll be connecting him again. The speaker will be joining in few minutes. He's facing some technical issues. Sir, can you hear us now?
I can hear you. So let me share my screen again. Just one second.
Okay, sir.
So is it visible now?
No, sir. Yes, sir, it is visible now.
Okay. So yeah, so I think I was here. So I was telling that standard practice for handling large volume and dimensionality of the data set is to develop efficient algorithms using techniques like Hadoop and MapReduce. But in sketching and sampling techniques, our objective is slightly orthogonal. Here we try to compress our data set, basically turning big data into tiny data with provable guarantee. And these sketching and sampling techniques lead to scalable search, classification, clustering, and ranking performance. So basically, there are two parts in the talk. In the first part, we'll talk sketching algorithm for discrete data set, and which consists of two parts. In the first part, we'll talk about sketching algorithm for binary data, and in the subsequent part, we'll talk about sketching algorithm for categorical data set. And the third part of the talk, we'll talk about sampling algorithm for big data set. So yeah, so this is first part of the talk. We'll be focusing on developing sketching algorithm for sparse binary dataset, and here I'll talk about our paper, efficient sketching algorithm for sparse binary data, which is joint work with Debajyoti Bera and Karthik, and got accepted in IEEE ICDM. So we'll be focusing in this part. We'll focusing on the high dimension and sparse binary dataset. So basically, text documents are commonly represented using bag-of-word representation. So, and typically bag-of-word representation gives high dimension and sparse binary vector. So basically, in bag-of-word representation, we have given a set of documents. We take union of important words, which gives us a dictionary. And this dictionary dimension of the data set determined by the size of the dictionary. And typically in any documents, the number of words is pretty small, but the dictionary size could be pretty large. So each representation of document in bag-of-word model gives high dimension and sparse binary vector. And typically using the same technique, bag of visual words representation of images gives high dimension and sparse binary vectors. And typically due to Kursnov dimensionality, these representations getting insight from these representation of data set, it's pretty cumbersome. And typically in algorithms like clustering, classification, nearest neighbor search, and ranking, they scale poorly with respect to dimensionality of the data set. And now, and the remedy for this thing is to perform compression or dimensionality reduction. And what sorts of guarantee shall we expect from a compression algorithm is that distance and similarity between every pair of points is approximately maintained after compression. And in this talk, we'll be in this part of the talk, we'll be focusing on binary to binary compression. Basically, our input is high dimensional binary vector, and our output is low dimensional binary vector. And the reason being because the binary representation is space efficient. And we will be focusing on the following 4 similarity measures, such as Hamming distance, cosine similarity, Jaccard similarity, and inner product. And we'll evaluate our compression algorithm on the following parameters. So the first parameter is compression time. So basically, this is the time required by the compression algorithm. And the second one is the space required to store the sketch. This basically consists of 2 parts. The first one is the dimension of the data post dimensionality reduction. And the second one is the number of bits required to store the value of each feature. And the third part is the number of random bits. So since most of these sketching algorithms are randomized and which require random seed for performing dimensionality reduction. So basically, we want all these three, the input required by all these 3 parameters to be as small as possible while maintaining a desired accuracy. And what do we mean by accuracy will be clear in subsequent slide. So by the way, feel free to interrupt me in between if you have any questions. And let's try to make the this thing a bit more interactive. So now, the thing is, one may ask, there are several dimensionality reduction algorithms available. So why should we look for any particular for sparse binary data set? So for example, the standard dimensionality reduction algorithms such as JLMA and PCA, they are not binary to binary. Basically, after sketching, they may not maintain the binary version of the data set. And also, it is not clear if they like preserve all these similarity measures such as Hamming distance, inner product, cosine similarity, and Jaccard similarity in the sketch representation. And the second option is like, since the data set is sparse, why don't we store non-zero indices? And typically, storing non-zero indices will require S log d bits, where S is the sparsity of the input, because in each feature, to store each value of each feature, will require log d bits, and since the data set is S sparse, so it will require S log d bits, so which will be infeasible when the d is pretty large. Basically, if d is of order millions and higher, even storing non-zero indices will be expensive. So now this is one of the most important slides for this part of the talk. So here we'll talk about our result, binary data sketching or bin sketch. So basically our algorithm is very simple. Our input is a d-dimensional binary vector, and its sketch is capital N dimension, where capital N is much smaller than d. So basically there are 2 parts. In the first part, we designate mapping from d to n. So basically for each feature from this d, we randomly assign it to from 1 to n. So for example, for this feature, we'll generate a random number from say 1 to n. Suppose it comes as 2, we'll assign this feature with this guy. Similarly, for the second feature, we randomly generate a number from 1 to n. Suppose its value is 2. So we'll assign the second feature with this guy. So similarly, for each feature from 1 to d, we'll randomly assign it to from 1 to n. So, and this mapping will be fixed for all the data points. Now we need to use this mapping to generate sketch of our input. So basically what we do, suppose our say one data point is 001001010. So we'll see using this mapping in each bucket what all entries are getting getting in. So for example, in this bucket, we get value 1, 0, and 1. So we take the bitwise OR, and whatever is the corresponding value, we'll assign it to this bucket. Similarly, for this feature, we get value 0, 0, and 0, and their bitwise OR is 0, and the corresponding value will put in over here. Similarly, for this feature, we'll get value 1 and 0, and the corresponding bitwise OR is 1, so we'll put it over here. So by doing, say, random bucketing and bitwise OR, we get the sketch of the input, which is 101 in this case. So any doubt with this this sketching technique?
Participants, if you have any doubt, you can raise your hands and we will unmute you.
Or you can just directly unmute and interrupt me in between. So that will be, I think.
Sir, actually, chat and as well as mic has been disabled for all the participants, so that you may not get interrupted like that.
Okay.
So.
Actually, currently attendees are in very huge number. That's why we have disabled the chat.
Acha, okay.
Currently, it is around 500.
Okay. Okay.
Yes, Khushbu, you may ask your query. Unmute yourself and ask your query. Saurabh Kumar.
Hello. Hello.
Please ask your question.
Good morning, sir.
Good morning.
The question is that how you had selected this in this tab. We are seeing that you had opted 0, 0, and 0. And these things are going randomly, or you are applying some algorithm to select these, just like 0, 0, and 0. How are you selecting these types?
So these are just for illustration. So basically, in the mapping, there are two parts. In the first part, we randomly assign this feature of each feature from 1 to D to 1 to N. And in the second part, this is just for illustration. Suppose our input is this this data point, and if we use this mapping, we'll get this sketch vector. So basically, we'll see under this mapping what all bits are falling in each feature, sketch dimension, and we take the corresponding bitwise R. So this is just for illustration.
Sir, but if we change the consequence of the mapping, then it will directly affect the accuracy, no? So how will get the optimum?
Okay, so basically, so there we need to carefully choose the value of n, so that this value of n determines our accuracy. So that how to choose n we'll see in in a minute. Thanks.
Okay, thank you, sir. Thank you, sir.
Okay. So yeah. So and interestingly, this simple algorithm gives a one-shot compression while preserving multiple similarity measures such as inner product, Hamming distance, Jaccard and cosine similarity in the same sketch. So I'll just try to give some theoretical insight for our algorithm. So first we'll see, using this our approach, how can we estimate the number of ones from the sketch. So this portion is our input vector, which is of D dimension, and this portion is our sketch vector, which is of capital N dimension. And you can think of this this red color region as the number of set bits, number of ones, and this red region as the number of set bits. And our input is U, and its sketch is US. And this mod of U denotes the number of ones in input vector. So, so since our mapping is random, so probability that some ith bit of US is 0, it will be 1 minus 1 over n raised to power number of ones in U. So with probability that any particular bit is set will be 1 over n, and probability that that particular bit is not set is 1 minus 1 over n, and that particular bit is set by considering all the number of ones in the input vector, it will be 1 minus 1 over n raised to power number of ones in U. And the probability that that particular bit is 1, that will be complement of this expression. And now we'll calculate the number of ones in expected number of ones in US. It will be n multiplied by this expression. And now we'll solve this for number of ones in U. We'll solve this for mod of U, because this is the number of ones in our input vector. So here basically what we are trying to do. So now our we have given our input vector u, and we used our bin sketch. We get the US, and from US we'll estimate the number of. We are estimating the number of ones in u. So the number of ones in u is determined by this expression, which we obtain by solving this expression. And now, since we don't know this E of expected value of number of ones in US, but rather we know the observed value of number of ones in US, which is NUS, then we'll just replace this expression by NUS, which is the number of ones observed in our sketch. So, and this is our estimate for the number of ones in U from the sketch. So this is log of 1 minus NUS over N by log of 1 minus 1 over N. And now we need to show that this is our estimate, whereas this is the actual quantity. We need to show that our estimate closely approximates its original value. And this can be shown via concentration inequality. So basically, we can this experiments can be thought of as throwing mod of u balls into n bins, and the expected number of non-empty bins is concentrated along its expected value using concentration inequality. And now if we set n as order of number of ones in u raised to power 3 over 2, then by some algebra we can find that the difference in our estimate versus the original quantity is at most square root of number of ones in u. So basically, the thing is that, like, the summary is, if we use our algorithm, and we then the number of ones estimated from the sketch is like it gives close approximation to its ground truth value, and the error is pretty small, like it's order of square root of u, right? Now we'll just try to extend this for inner product similarity. So we'll just try to extend the same analysis for inner product similarity for a pair of vector. So again, our input vector is u and v, and the corresponding sketch are US and VS. So now what we need to do, we'll just we are now trying to compute the probability that ith bit in both US and VS is 1. So this probability can be splitted into two parts. That say ith bit, say this region, is set due to the same number of bit which is set in both U and V, right? So you can think of this like shaded region as the set bit, like the bits which are 1, and the unshaded region you can think of as 0. So this is just for pictorial representation. So this region is set with probability 1 minus 1 minus 1 over n raised to power intersection of size of intersection or dot product between U and V, by following the same analysis that we saw in a couple of slides back. And now there is another event. Basically, the same bit is set. So basically, this bit is set due to the bits which are set in U, but not in V, right? So basically here, the same bit is set in both US and VS, but the bit which is set in US is set due to some particular bit which is set in U, but not in V. And similarly, the bit which is set in VS, that is due to some bit which is set in V, but the corresponding bits are not set in U, and its probability is 1 minus 1 over n raised to power dot product of U and V, basically complement of this event into 1 minus 1 over n raised to power U not V. So this is the bits which are set in U but not in V, and bits which are set in V but not in U, right? And now we'll just try to compute the expected number of bits which are set in both US and VS. So we'll just multiply this expression by n. And now we need to just solve this expression. We are just solving this expression for u intersection v. So basically u intersection v correspond to the dot product of u and v, and we need to determine this size of u intersection v. So we'll just solve this for u intersection v, and we obtain this expression, right? This ugly looking expression. And using this expression, we'll just try to compute the inner product between u and v from the corresponding sketch. All right. So, but now here we don't know several quantities which are mentioned in this expression. For example, this number of ones in u, number of ones in v, and expected value of us intersection vs. But we know how to estimate them. Basically, that's what we saw in a few slides back, how to estimate the number of ones in u from the corresponding sketch. So this is what we'll use the same technique over here to estimate the number of ones in u and v from their corresponding sketches. And for this term, dot product between us and vs will replace with the corresponding entity that we observed in the sketch, and then our estimate is this one. So basically, in the previous, so in this slide, whatever expression are mentioned here, we are just replacing them with our estimates. So basically, we are replacing mod of u by this corresponding estimate, and this expected value of size of us intersection vs by the corresponding quantity which we observed from the after applying this algorithm on our input. Right. So this is now we get this is our estimate for the inner product. Now we need to show that this estimation is like closely approximates the corresponding ground truth value. So after doing some basic algebra, we got the following. So basically, if we set n as s raised to power 1.5, basically order of s square root of s, where s is the sparsity, then with high probability, we are able to show that the difference between our estimation of inner product with respect to its ground truth value is smaller than order of square root of s. All right. So basically, so this requires some careful algebra, but we are just skipping it due to interest of the time. So I'm just trying to give the high level idea. And so this is for a pair of point, and we can easily extend it for a set of a data set which consists of m point by just multiplying this ns, basically s raised to power 3/2 log m. By just log m overhead in n, we can extend this for a set of a data set which consists of n points and offering all pair guarantees. Right? And so this analysis we did for inner product, but interestingly in binary data set, all these four similarity measures are closely related with each other. So basically, for say two data points u and v, the Hamming distance between u and v is equal to number of ones in u plus number of ones in v minus twice of their inner product. Similarly, the Jaccard similarity between two data point u and v is equal to the ratio of inner product by inner product plus Hamming distance, and similarly cosine similarity is ratio of inner product by ratio of square root of the norm of the input point. And since we know how to estimate the number of ones in u, number of ones in v, and the inner product, we can estimate the Hamming distance, Jaccard similarity, and cosine similarity, and so on. All right. So now we'll just try to illustrate some experimental result for our proposal. So here, what we are trying to do, we are just trying to compare our algorithm with other like algorithms which are used in practice for these purpose. So we are using for cosine similarity, we are using sine random projection, and its recent advance, which is circulant binary embedding. And for Jaccard similarity, we are using minwise independent permutation or minhash, and its recent advance like DOPH and odd sketch. And we are also comparing it with our earlier work, which is BCS. And we are running it on this bag of data set, which is of say dimension 1 lakh to 7,000, and they are reasonably sparse. Right. So, and we are using mean square error for our like estimation purpose. So basically, what we are in our experiments, what we are trying to do, basically we wanted to understand the behavior of our algorithm in different similarity regime. So to do so, we extract similar pairs. Basically, we extract the pair of points whose similarity is higher than certain thresholds, and then we compress our data set to various dimensions, and then we calculate the MSE, basically, which is computed by the following. So basically, what we did, we calculate the square of the difference between the estimated similarity on the compressed data set and its corresponding ground truth value, and we add it for all pair of points, and we calculate the mean. And since we are focusing on Jaccard and cosine similarity, so this value will be smaller than 1. So, but to just magnify the value, we compute the negative log base C value. So, so essentially, we are computing the negative log MSE. So, this negative log MSE, a higher value is indication of better performance. Yeah. So this is our experimental plots for Jaccard similarity on NY times data set. And here the red curve correspond to bin sketch algorithm, and others are min hash, odd sketch, and DOPH, and so on. So here higher value correspond to better performance. So you can see that our red curve is closely overlapping with min hash, and which is kind of state-of-the-art algorithm for Jaccard similarity. So basically, in every threshold region, our performance is comparable to min hash, and this is our result for cosine similarity. And here we observe that our performance is better than the remaining algorithm, at least on majority of reduced dimension. And the most important thing is the running time. And our for other baseline algorithm, their running time is kind of linear with the reduced dimension. So x-axis correspond to the reduced dimension and y-axis correspond to the time in second. So for other baseline algorithm, we can see that as we increase the reduced dimension, the time is the running time, corresponding running time of the baseline algorithm is increasing linearly. Whereas for ours, it is kind of coinciding with x-axis. So basically, on all these data set, our running time remains within few seconds. Whereas for others, it may like higher than maybe 1,000 seconds for majority of the baseline algorithm on NY times data set. So any question on this part of the talk? So basically, now I just concluded the first part of the talk, which is sketching algorithm for sparse binary dataset.
Please raise your hands if you have any questions, and we will unmute you.
Yeah.
Does anybody have any question? Saurabh Kumar, you may unmute yourself and ask your question.
Hello.
Yeah, yes, Saurabh.
Sir, you talked about Bean Sketch. We had already seen Bean Sketch, the working, how it is working, but we are not aware about how BSE working, Minhash working, or Odd Sketch working. Kindly give a brief idea about that so that we can do a comparison between among them.
So I think it may be a little difficult to like include all these baselines for illustration, but you can think of like SimHash is kind of state-of-the-art algorithm for cosine similarity. So basically, SimHash takes real valued data points as input and outputs binary vectors, and so that from the binary vectors we can closely approximate the corresponding original cosine similarity. And similarly, Minhash takes real binary vectors as input and compress them so that from the compressed vectors we can estimate the Jaccard similarity. And CBE and DOPH are their corresponding faster version of SimHash and Minhash. Right. And BCS is our previous algorithm, and the bin sketch is kind of slight improvement of BCS.
Sir, how the efficiency of algorithm get increased? What the changes you had made in the BCS then it get to Bean Sketch?
Sorry, come again.
Sir, how the efficiency get increased? You said that ki BCS is our previous model. We had proposed that, and later on, after some improvement, we are currently on Bean Sketch. And what are the improvements you had done, sir?
Okay,
Slightly
so
overview I want.
So as far as time is concerned, these two, the running time of bin sketch and BCS, they are kind of comparable. So in this plot, they are kind of overlapping with x-axis. So you can see that red and orange, red correspond to bin sketch and orange correspond to BCS. They are kind of overlapping with each other. But in this plot, you can see that BCS is lower than bin sketch. So basically, this orange color line is somewhat lower than the red color line. So basically, in this graph, higher value indicates a better performance. So this orange color line is below than red color line. It means that bin sketch gives much more accurate sketch than BCS. So bin sketch is more accurate, but but the speed wise, it is kind of comparable with respect to BCS.
Okay, sir. Thank you, sir.
Yeah. So if there are no further question, I'll move to the second part of the talk.
Yes, sir.
So in the second part of the talk, we'll focus on the problem of sketching algorithm for categorical dataset. And here I'll talk about our paper, which is dimensional reduction for categorical dataset, which is joint work with Debajyoti Bera and Vishnudev Verma, which is currently under review at TKDE. So in categorical dataset, in many features in our real world dataset correspond to categorical variables. For example, days in a week, months in a year, blood group, gender, and so on. So these values are kind of categorical values. So days in a week, such as say, Sunday, Monday, Tuesday to Saturday. So these are categorical variables. Similarly, months, blood group, and there are several other features which are considered as categorical variables. So here I'll just try to give a simple overview of how to represent the categorical dataset. So this is kind of our toy dataset, which consists of say only 4 features, say days in a week, month in a year, blood group, and gender. And suppose we have only, for simplicity, we have only 2 points in our dataset, U and V, and the features correspond to U are Sunday, Jan, A, and M. And similarly, features correspond to V is Monday, December, A, and F. Right. So the standard representation of for categorical data set is, so basically we can enumerate all these corresponding categorical values with a number. So for example, days in a week, it may take 7 values from Sunday to Saturday. And for each of these, we can give us one value from 1, 2, 3, 4 till 7. Similarly, month in a year, it may take 12 values. So for each of the month, we are giving one number from 1 to 12. Similarly, for blood group, blood group can take 4 values. So for each of these blood group, we are giving one number from 1 to 4. Similarly, for gender, we are giving from 1 or 2. So now under this representation, for you, the corresponding value will be 1, 1, 2, 1, because Sunday is represented by 1, Jan is represented by 1, and A is represented by 2, and M is represented by 1. And similarly for V is 2, 12, 2, 2. All right. Now the thing is, how should we like compute the similarity or distance between two categorical data points? So so the distance between two categorical data points are represented by Hamming distance. So basically, so we basically count on each places, on how many places the corresponding features are differing with respect to each other. So for example, in this case, only one value is same, and out of 4, 3 values are different. So basically 1 is not equal to 2, 1 is not equal to 12, 1 is not equal to 2. So we are just counting the place where the corresponding features are differing with respect to each other, and we are adding them up, and that is our corresponding Hamming distance. All right. So basically, this is just a simple illustration how we represent categorical data set and how we are computing the distance between two categorical representation. All right. So now the thing is, like, how should, suppose in our data set we have like which consists of categorical features, but the number of categorical features are pretty large. And again, we want to like come up with compression algorithm for categorical data set. Categorical data set. So one like simple proposal could be represent our categorical data set using one-hot encoding. So in one-hot encoding, what we do, so for each feature, so basically days can take 7 values, months can take 12 values, blood group can take 4 values, and gender can take 2 values. So basically each feature, corresponding feature, we just expand them with the number of possible values that it can take. So for example, day, we are representing it, we are just expanding it with 7-dimensional feature, and months we are expanding it with 12-dimensional feature. Blood group, we are expanding him into 4-dimensional feature, and gender, we are expanding it in 2-dimensional feature. And we are just setting one at the corresponding position, and the remaining are zeros, right? Similarly, for month, we are just whatever value is present there, we are just setting one at the corresponding position, and remainings are 0, and so on. So for example, for our vector u, which is 1, 1, 2, 1, we are putting 1 at this position, and 1 at this position, and 1 at the second position, and again 1 at the first position. And similarly for v, in one-hot encoding, we are putting 1 at the second position, and again 1 at the 12th position, and again 1 at the second position, and again 1 at the 1 position. Right. So now our categorical data point are represented as binary vectors, and now so from this binary vector we can directly compute the Hamming distance. Right. So Hamming distance between u0 and v0 is 6, which is twice of the original Hamming distance. Right. So basically now one naive approach could be So basically, given our categorical data set, will represent them using one-hot encoding, and this will give us high dimension sparse binary vector. And now we can just directly apply the bin sketch algorithm that we saw in the first part of our talk, right? But this approach could be impractical when the dimension of our categorical data set and the number of possible categories are large. So in this case, in this example, you can see that our original dimension of input point is 4, and after one hot encoding, its dimension got increased to 25. So this is just for illustration, but in practice, if we apply this one hot encoding, the dimension of our binary vector obtained after one hot encoding could be pretty large. And it may turns out that if the number of point is also large, our data set, it may not be possible to apply bin sketch because it may go out of memory, or we may get at least its runtime could be pretty large. So now our focus is to come up with an algorithm which can directly compress the categorical data set without going via one hot encoding and applying bin sketch on top of it. So this is our proposal, which is kind of, you can think of extension of bin sketch. So again, so our input is vector u, and the corresponding sketch is us. Our input dimension is d, and the sketch dimension is n, where n is much smaller than d. So again, so for each feature, similar to bin sketch, for each feature from 1 to d, we are randomly assigning it from 1 to n. So similarly, like for this feature, we'll just randomly generate a number from 1 to n. Suppose it comes as 2, we'll link this feature with this this sketch dimension, and so on. So we do this for each of the features from the input vector, for the input vector. Now we are doing one thing extra. So we are taking a prime number p, and we randomly generate a number from 0 to p minus 1. Right? So for each feature, we are randomly generating a random number from 0 to p minus 1, where p is prime number, which is sufficiently large, right? So for this feature, we are getting, say, R1. For this feature, we are getting R2, and so on. Now we have these list of RIs from R1 to RD, and this mapping from D to N. So now we'll use this mapping and these RIs for computing the sketch of the categorical vector. So, and the process is again similar to bin sketch, but one thing extra we are doing before bucketing these features, we are just multiplying them with the corresponding RI values. So for example, in this feature, this bucket, basically the first bucket of our sketch dimension, we are getting value u4 and u7. So we'll just multiply the corresponding values r4 and r7. So the value is, the sketch value is u4 into r4 plus u7 into r7, and whatever value we'll get, we'll compute its mod p, and the whatever result is get will be sketch value of corresponding to this dimension. Similarly, for this second feature in the sketch dimension, we are getting values, say u1, u2, and u5, and the corresponding sketch value will be u1 r1 plus u2 r2 plus u5 r5 into mod p, and whatever is the result is the sketch representation for the second feature. And we are doing this for all the features in the sketch dimension. So this can be thought of as a simple extension of bin sketch, but for categorical vectors. And in like one line, the idea is random bucketing mod p. All right. So now again, we'll just try to analyze this scheme and see how, like, what kind of guarantee that we get after applying this sketching algorithm for categorical data set. So again, you can think of U and V as our input point, and their input dimension is D, and the sketch dimension is capital N, and the corresponding sketch of U and V are US and VS. Right, and I'll just briefly like state the notation that we are using in this analysis. So small h denotes the Hamming distance between U and V, and F denotes the Hamming distance between US and VS, and US and VS are the sketch of U and V, and F star is the expected value of Hamming distance of US and VS. And we need one more notation. So suppose if we are focusing on this first feature of VS, which is the sketch of V, and its value is say V1 VI plus VJ RJ mod P. So we denote this F1 of VS, basically the first feature of VS, by the list of features which we obtain in from our input vectors. So basically, V of S1 is V1 VI plus VJ RJ. So the F1 of VS will be VI and VJ. So basically, what all features are getting falling in the first features, and so on. Similarly, we can do it for each of the feature in the sketch dimension, right? So now, so these Fi of US and VS can be thought of as set, basically, which consists of the features from the input which are falling into that particular bucket, right? So F1 of VS is again correspond to the features which are falling into the first sketch dimension of our VS. Similarly, F2 is the list of features which are falling into the second dimension of VS, and so on. Similarly, for Fi is the list of features which are falling into the ith bucket of US and VS, right? So suppose our original Hamming distance is H, and then Fi of US is not equal to Fi of VS. Basically, for ith feature, when the corresponding set of values which are falling into those buckets are not same, if and only if any of those positions that are mapped to I, we'll just try to calculate this probability. That probability that Fi of US is equal to Fi of VS is equal to 1 minus 1 over n raised to power h. And this is again using the similar analysis that we saw for bin sketch. And this probability is over the choice of the mapping from D to N. And again, the probability of under the choice of pi and r are correspond to this random vector which we are choosing for each of the features for our input vector. So probability that U of Si is equal to V of Si, basically ith feature of both US and VS are same, but given that Fi of US is not equal to Fi of VS, basically their values are which are putting into the corresponding features of the sketch US and VS, they are different, but the sketch value is same, and that could happen because we are applying the value mod p after taking addition with the multiplying them with corresponding RIs and taking the mod p. So probability that U of Si is equal to V of Si, given that Fi of US is not equal to Fi of VS, is equal to 1 over p, right? So now again, like similar to bin sketch, we are trying to will calculate the probability that U of Si is not equal to V of Si. So we'll just expand this using conditional probability. So this can be expanded into two parts. In the first part, it is equal to probability of U of Si not equal to V of Si, given that Fi of US is not equal to Fi of VS, into the probability of Fi of US is not equal to Fi of VS. Simple conditional probability. We are expanding this using conditional probability. And the second event is probability of U of Si not equal to V of Si, given that Fi of Us is equal to Fi of Vs into the corresponding probability of Fi of Us equal to Fi of Vs. And now this the term which I mentioned in the green font, it can't happen, because if Fi of Us is equal to Fi of Vs, essentially their sketch value will be same. So this then its sketch value will be same. So this term will be equal to 0. So only this first part in our conditional expectation will contribute towards the probability of U of Si is not equal to V of Si, and its value will be 1 minus 1 over P into this 1 minus 1 over 1 minus 1 minus 1 over n raised to power h. Now again we'll just calculate the expected Hamming distance. So this is the probability that a particular one particular bit in both US and VS are different, and the corresponding Hamming distance will be, if we multiply the corresponding Hamming distance we obtain by multiplying this expression with n, which is the sketch dimension. And again this is our expression of expected Hamming distance, and what we want is h, which is the original Hamming distance. So again we'll solve this expression similar to what we did in case of bin sketch for h, right? So this is our expression once we solve this for h, and its value is log of 1 minus f star, which is expected Hamming distance between US and VS, by n into 1 minus 1 over p by log of 1 minus 1 over n. And since f star is the expected value, we'll replace it with the corresponding value that we observed. Right. So the corresponding observed value is f, and we show that similar to what we did in case of bin sketch using concentration inequality, this f star, which is expected value, is sufficiently close to the corresponding value which we observed in the sketch. And so thus our estimator is h hat, where we just replace this f star, which is expected value of Hamming distance between US and VS, with the corresponding value that we obtain from the sketch, right? And this is our estimator. And again, after doing some like kind of heavy algebra, we are able to show that if we choose n as 4s, basically you can think of this as order of s, where s is the sparsity of input, then the probability of that the difference of the Hamming distance between our estimate and the ground truth will be like smaller than this expression, which is essentially, you can think of this as order of square root of s. This will be smaller than order of square root of s with high probability, where delta takes small values. So basically this the probability that their value is the difference in the difference between our estimate and the corresponding ground truth is small, will be with high probability, and this is what we want. So our error is small with high probability. And now you can think of you can see several expression over here, like p and delta and so on. So delta is parameter for probability, and typically we can think of delta as say 0.1 or 0.001, and p is a prime number which is sufficiently large. And basically we need to choose p such that this term 1 minus 1 over p should be greater than 4 over square root of s into square root of log 2 over delta. And essentially, like we can take p equal to 2 as well, and this will be sufficient for like when our sparsity is say maybe close to 1000 and delta is say 10 raised to power minus 4. And interestingly, our result is that we obtain is independent of the number of categories. Right? Yeah. And one more interesting property of our proposal is that it maintains the sparsity. Our sketch maintains the sparsity of input. So basically, if our input is sparse, then the sketch obtained via our proposal will be sparse. So the expected number of non-zero entry in the sketch will be at most, it should be S over 4. So if our original sparsity is S, then the sparsity of our sketch will be at most S over 4. So now we'll just see some experimental work for our algorithm. So here we try to run it on slightly more higher dimensional data set. So we mostly use the data set from bag of word, which is of say dimension 1,28,000 and so on. But we particularly use one very high dimensional data set whose dimension is close to 13 lakh. And we use several baselines such as one-hot encoding plus bin sketch, sketching via stable distribution, feature hashing, and so on. Several other like known sketching algorithm. And our first evaluation is on RMSE. So basically in RMSE, what we do, we calculate for each pair of points, we calculate the difference between the estimated quantity and estimated Hamming distance and the corresponding ground truth Hamming distance. We compute the difference, take the square, add it for all pair, and take the mean. So this is note that this is RMSE, whereas in case of bin sketch, we were using negative MSE. So here the lower value is better. So here you can think of our F sketch is represented by a red color plot, and its value is much lesser than the corresponding baseline. So basically, it is able to like closely approximate the ground truth Hamming distance, whereas for others, their like error is pretty large. And recall that the dimension of brain cell dataset is 13 lakh, and you can see that we are able to compress them into maybe 1,000, and even on 1,000, it is giving like very good approximation to the corresponding pairwise Hamming distance. Right. So just to summarize, like this our proposal F sketch is able to compress say high dimension data set. So for example, data set of dimension 13 lakhs to very few a few thousand dimension sketch while preserving the pairwise Hamming distance. And again, our main advantage, one of the main advantage of our proposal with respect to the baseline is that the runtime of our algorithm is extremely fast. So you can see that on brain cell dataset, the proposal that I mentioned, one-hot encoding plus bin sketch, it went out of memory, and whereas for others on other dataset, our speedup is significantly fast. So here we are computing the speedup with respect to the reduced dimension 1,000. So on NY times dataset, we got around 5,700 times speedup and so on. And so these are two baseline algorithm, sim hash and feature hashing. So their running time is comparable to ours, but these algorithms are not meant to apply for categorical dataset. So basically, we just ad hocly use them and see how they are performing with respect to bin sketch. And their runtime is comparable, but if you see in RMSE slide, their RMSE value is significantly worse than ours. So this is our correspond to F sketch, whereas these two like orange and green color font plot correspond to feature hashing and sim hash. So the gap between red and orange and green are much prominent. So basically, we are able to closely approximate the ground truth similarity at much higher speed. So we also evaluated our proposal on clustering tasks. So in clustering task, what we did, we we run clustering algorithm on full dimension dataset and like discovered the ground truth clustering result, and then we compress our dataset on using various baseline algorithm on different values of reduced dimension, and on those reduced dimension we perform the clustering, and we noted the corresponding, we compare the corresponding clustering result using the purity index. So typically purity index is one of the standard metric for measuring the clustering quality, and its value is between 0 and 1. So closer to 1 is indication of better performance. So as we can see that on Enron dataset, our purity index is much higher than the remaining baselines. And similarly for on KOS and other dataset, it is kind of comparable or maybe best with respect to the baseline algorithm. And similarly, we also performed evaluate the performance of F-sketch on similarity search experiments. So here what we did, we split our data set into two parts, 10% and 90%. So 10% part is called as query partition and 90% is called as say validation partition. So for each data point in the query partition, we compute the closest 100 point, which is our ground truth, and then we compress our data set using baseline algorithm to various dimension. And for each of these QIs, we listed the closest 100 point in the compressed dimension. And suppose O correspond to the ground truth result and O prime is the result on the compressed data set. And then we measure the accuracy using by computing the difference between the set O intersection O prime by size of O union O prime. So essentially it is Jacquard similarity between O and O prime. So its value will be 0 and 1. So closer to 1 is correspond to better performance. Okay, so again here we can observe that the F-sketch, which correspond to red line, it's giving comparable or better accuracy with respect to many of the baseline algorithms. Right. So there are several potential application of our work. So basically we can use this bin sketch and or F sketch depending if our data set is binary or categorical, and we can use them for faster deduplication. So basically we can compress the data set using bin sketch or F sketch, and then we can perform clustering or indexing. And similarly we can use it for scaling up performance on clustering data. And so basically again we can just compress the data set using bin sketch and F sketch using k-mode and then run k-mode clustering or spherical k-means clustering. And we can also use it for a frequent item set mining problem. So basically we can compress our data set using bin sketch, and we can run B standard algorithm for frequent item set mining, such as a priori algorithm, and so on. So this is how like I concluded the second part of the talk. So I'll just try to rush up the third part. If you have any question, just please feel free to interrupt and ask.
Yes, Naveen, do you have any questions? Please unmute yourself and ask your question. Sumit Kumar, do you have any query?
Yes, Sumit, you can ask.
I think we can proceed further.
Naveen and Sumit, please unmute yourself and ask the question. No questions, sir. You can proceed.
Okay. So now we'll go to the third part of the talk. So here we'll focus on the problem of k-mean clustering in presence of outliers. And here I'll talk about our result, which is robust k-means plus plus, which is joint work with Amit Deshpande and Puneet Kacham, and which got accepted in UAI. So basically, what is clustering? So in typically, as we know that in clustering, we have given unlabeled data set and we need to organize our data points in such a way in several clusters such that each cluster will have, they follow high intra-cluster similarity and low inter-cluster similarity. So basically, it is kind of aim to find the natural grouping among data objects. So we'll focus on Euclidean k-means problem. So in k-means clustering problem, we have given a set of n points in d-dimensional space and a number k, and k determines the number of clusters. And our output is to find a set of k cluster centers such that it minimizes the following objective function. So objective function is computed by computing the distance of each point with respect to its nearest cluster center and computing the sum, computing the square and add it for all the points. So this is like sum over x in x, and we compute the minimum of x minus c square, where c is from our cluster centers. And this is our clustering cost. Right, so essentially we have given unlabeled data set and our aim is to group them using k-means clustering. So for each so each data points belong to one of the clusters and the cluster is identified by the cluster centers, and basically we need to minimize this potential function. Right. And this problem is NP hard. So basically it's if you want to find the optimal clustering result, then it may take time which is exponential in the input size, and it is NP hard even for very trivial case of input when say k is equal to 2. Basically when there are only 2 clusters in our data points and when d is equal to 2. Basically when all the points are in plane. So even on these two simple cases, this problem is NP hard. So now we'll just quickly talk about some standard clustering algorithm for k-means. So one of the popular algorithm is Lloyd's algorithm. So here what we do, we just start with a random initial set of clusters and cluster centers. So basically we have given set of points, we randomly sample few points, and then we consider those sample points as cluster center. We assign all the points to the nearest cluster center. So that we are doing in this, we are trying to explain this in the scenario. 3 represented by say violet, green and yellow color, and then we assign all the points to the nearest cluster center. So basically these partitions correspond to the points which are closest to their respective cluster center, and then we compute the mean, and then we just repeat it. And basically we compute the mean, we again do the assignment, and then update the cluster center and so on, and we'll iterate until we don't see much improvement with respect to our previous iteration. All right, so this is one of the classical algorithm for k-means, but the result that we get using Lloyd's algorithms may not be close to optimal. So suppose consider the following scenario. When we have say two set of clusters, and one consists of say 100 point and second consists of say 1 million point, and if we sample points randomly, so most likely we're going to hit maybe the heavy clusters. So basically so if we sample 2 points, so most likely we'll going to hit the heavy clusters which consist of 1 million point. And now if we do the assignment, so we'll get one cluster of this yellow color, and the remaining point will be another cluster. But essentially, the optimal clustering will be the one cluster which is of 1 million point, and the second cluster which is of consists of only 100 points. Right. So, sir, how much time I have?
You can take your time.
Okay, so yeah, so maybe I'll take maybe 10 minutes. So
no problem.
Okay, thank you. So the idea of this Lloyd's for this slide is that Lloyd's algorithm, although we use it in practice, but the result that we can get may be very far from the optimal. So essentially, when the optimal the underlying clusters are very non-uniform. So basically, one cluster consists of so many points, and another cluster consists of only few points. Right. So to overcome this problem of Lloyd's algorithm, so there is another sampling algorithm for k-means, which is known as k-means plus algorithm. So in k-means plus algorithm, we start. So suppose C is correspond to our set of cluster center. We start with say C equal to empty, and now in each iteration we'll sample 1 points. So and basically we'll iterate it k times, and each iteration we sample 1 points, and so by doing it k times we'll get set of k points, which is our representation of the corresponding cluster centers, right? So in the first point is sampled uniformly at random. So suppose we are sampling the first point like randomly, and for example, suppose we hit say this point, and the red point correspond to the sampled point. And for the second points, we generate a probability distribution, which is minimum of the like R correspond to the set of points in our data set, and C correspond to the corresponding cluster centers. So basically, we pick a point R with probability proportional to minimum of C in C R minus C square. So basically, for once we have sampled the first point, we generate a probability distribution, which is the distance between the sampled point and the remaining points. So obviously, the points which are closer to this sampled points, the probability of getting picked as next cluster center will be smaller. So most likely we're going to hit point which is much farther than the first sample point, right? So again we sample the second point. So now we need to sample the third point, and to do it again we need to generate a probability distribution, which is the minimum for each point. We'll calculate the minimum of its distance with respect to the first two sample points. So again, the points which are over here, their probability of getting picked will be smaller because they are close to this cluster center. And the points which are over here, their probability of getting picked will be small because they are closer to this cluster center. So most likely we're going to, and the probability which are over probability of getting picked of these points will be higher because they are farther from these two already sampled cluster centers. So most likely we're going to hit this cluster center. So essentially, like k-means plus sampling distribution ensures that with high probability we are going to hit each cluster centers, and there is a and then on top of that we can do the iteration that we do it in Lloyd's or k-means clustering. And the guarantee that we get even after the sampling k cluster centers using k-means plus sampling distribution is that suppose we sample k points and we compute our objective function, so it is sufficiently close to the k-means cost with respect to the optimal clustering. So it gives a log k approximation in expectation, and it can be boosted to say some constant factor approximation or 1 plus epsilon approximation by picking say slightly more cluster centers and then solving a weighted k-means problem on these sampled points. So essentially, this k-means plus plus is like one of the fundamental algorithm used for k-means clustering, and it is I think also available in scikit-learn as a package. So yeah. So now our problem is slightly different. So basically, so typically we can assume that in our data set we may have several outliers, and ideally we would like to do clustering only on inliers but not on outliers. So here in this slide I'll just try to define the problem statement. So in our input we consist of say n points in d-dimensional space and an integer k, which is represent the number of clusters, and we have an outlier parameter which determines the number of points which are outlier, and our output is to find a set of k cluster centers that minimizes the k-means cost. So this is the k-means cost, but only on the inliers. So basically we need to iterate it over all the subsets of 1 minus beta n points. So beta determines the fraction of outliers. So the inliers will be 1 minus beta n. So basically we need to compute k-means cost, but over all possible subset of this 1 minus beta n point and pick the best solution. And again, k-means is hard, this k-means with outlier is again harder problem. So it is at least as hard as k-means. So it will be finding the optimal solution in polytime is not possible. So again, we need to go for approximate solution for this problem. Right. So basically, so in this scenario, suppose we have these data sets, and suppose we have say 3 outliers. So basically, we want to clusters only on only these inliers. So yeah, k-means with the k-means with outlier problem is also well studied, but there are not many practical algorithm for this problem. But also, like as this k-means with outlier problem is very standard and encountered in practice. But most of the results that are available, they are not like they are mostly theoretical and cannot be directly useful in practice. So, but our aim is like we want to solve this k-means with outlier problem using k-means plus plus sampling distribution. And the reason of picking k-means plus plus sampling distribution, because it is used in like almost all practical versions of k-means problem. So such as when it is used in scalable k-means plus plus, basically the case when the points are distributed in different machines. So it's kind of a distributed k-means. We have used like k-means plus plus sampling distribution, and even on streaming k-means. Basically, when we get points in stream, we use the streaming k-means algorithm, use k-means plus plus sampling distribution, and the faster variant of k-means plus plus also uses k-means algorithm. So basically, all these implementations are practical implementation, and they use k-means plus plus sampling distribution. So basically, we also want to solve this k-means with outlier problem using k-means plus plus sampling distribution, so that our result is practical and it can be used in practice as well. Okay, so now we'll see if we just naively try to apply k-means plus plus sampling distribution for k-means with zero outlier problem, what is going to happen. So suppose this is our scenario. So we'll sample first point uniformly at random. So suppose it hit this cluster. Now, since there are outliers in our data set, and suppose these outliers are very far away from the inlier clusters. So in say k-means plus plus sampling, we generate a probability distribution where point is picked based on the probability proportional to its distance from the already sampled cluster center. So most likely it is going to pick this point as next cluster center, but it is outlier. And now after Once we have sampled this cluster point, this outlier as a cluster center, and no matter what we do, our result will be significantly worse than the corresponding optimal solution for k-means with outlier. So basically, the summary is like k-means plus sampling distribution is prone to pick outliers when they are very far away from inlier clusters. Right. So now we'll just try to build intuition for our proposal. So in k-means plus sampling, it prone to pick points from clusters, but it prone to pick outliers as well when outliers are very far away from inlier clusters. And on the other hand, we have random sampling, which is not prone to pick outliers, but it prone to pick points from heavy clusters, right? So on one way, the advantage of k-means plus is that it picks point from the clusters, but the disadvantage is that it's prone to pick outliers when they are very far away from inlier clusters. However, on the other side, there is a random sampling algorithm, which don't pick outliers, but it performs very badly when we have clusters of non-uniform size. So each of these sampling distribution has one advantage and one disadvantage. So we just try to combine them. Our proposal is to combine them so that we can keep best of both worlds. So our proposal is the mixture of k-means plus and random sampling. So basically, in each step, we pick a point R with probability proportional to half of d square sampling. D square sampling is essentially k-means plus sampling, and half of uniform sampling. So instead, so what we sample is phi of RC by twice of phi XC plus 1 over 2n. So this is what we are going to sample with this probability. Instead of this is what we do in case of k-means plus sampling. So basically, our proposal is extremely simple. It is just taking the mixture of k-means plus and random sampling distribution, and after doing some algebra, this is what we get. So basically, we sample a set of k over delta points using the mixture of k-means plus and uniform sampling distribution, where delta is one parameter between 0 and 1. So essentially, we are sampling k over delta points. So like it is slightly more than k points, and we discard slightly more than the required number of outliers. So basically, we sample slightly more points and discard slightly more outliers, and then we sample k over delta points using the mixture distribution. And once we have sampled k over delta points, we identify the farthest beta plus delta n outliers and discard them and compute the clustering cost. And we show that clustering cost gives constant factor approximation with respect to the optimal k-means clustering over inliers. And its running time is nkd over delta. So essentially, it is linear in n. All right. So and in practice, so since in our proposal we sample k over delta points, which is slightly more than k points, and we can pick k points using weighted k-means plus sampling. So basically, for each of these points in that we sampled using our mixture distribution, we assign weights to each of the point, which is the number of points closer to those sampled points, and then we run weighted k-means plus and pick the best k points. Right. So in the interest of time, I skipped the experimental result, but we performed our experiments on several real-world and synthetic data set, and we compare it with k-means plus random sampling and other state-of-the-art algorithm for k-means with outlier problem, and we obtained comparable accuracy with respect to the state-of-the-art algorithm, while simultaneously achieving the significant speed up with respect to running time, because we are using k-means, some modification of k-means plus distribution. So like get the simplicity of K means simplicity and the faster running time as an added advantage, and at the same time our result is comparable or better with respect to the several state-of-the-art algorithm. And this is all I had for today, and thank you for your time, and now I'll stop here for your questions.
Participants, if you have any query, please ask.
Please raise hand if you have any query. Yeah, Akash.
Akash, unmute yourself and ask your question.
Hello, am I audible?
Yes, yes.
Yeah, so thank you, sir, for a good session. I had two questions. Actually, I was trying to unmute myself over here, but was not able to raise my hand. So it was around the application of bin sketch, how we can use bin sketch and a priori algorithm together.
Okay. So basically, in you can think of this transaction data set as binary data set, where your rows correspond to transactions and column correspond to the items, right? And so you can think of these this as a data matrix, and corresponding to columns, you can see like binary vectors, right? And for 2 points which are say highly similar, if their dot product will be high, like the corresponding, they are matching one in the large number of positions. So this is what a priori algorithm does. So it take all the pairs and compute the dot product, and for those pairs whose dot product is higher, it mention them as say frequent pairs, right? And the disadvantage of a priori will be that it need to run over all the transactions. So instead, what we can do, we can just compress it using bin sketch. And then we can run the a priori algorithm. And since the bin sketch closely approximates the dot product, so it will approximate the frequent pairs and subsequently other like higher order pairs, higher order subsets of items.
Okay, got it. Got it. So one follow-up question to that. So this is regarding the k-means algorithm. I was reading and researching, and I found that there is one elbow method which helps in estimating the ideal value of k. Is there any other method which is better than the elbow method?
Okay, so even elbow method, people I think use it as a heuristic. So yeah, so elbow method need not to give the optimal value of k. Uh, so yeah, so getting optimal value. So this k means problem is slightly weird in some sense. So even if we given k, finding the optimal cluster center is hard, and even on top of that, the finding the right value of k is also hard. So elbow method, to my knowledge, is heuristic, and other than that, I'm not sure. So I don't know the answer of this question.
Okay.
Need to check that.
Thank you, sir.
Yeah.
Bhavesh, quickly we have your question. Bhavesh, please proceed with vote of thanks, Vishaka.
Am I audible?
Yes.
Okay. Thank you, Dr. Singh, for this insightful lecture on sketching and sampling techniques for big data. This lecture was attended by more than 500 participants, and we are grateful to you for covering this topic in such a comprehensive way. It was truly edifying, and I hope that it would have benefited our participants in one way or the other. To express our gratitude, we would like to present you with a virtual memento. Ankit?
Ritesh, sir, can you change the slide?
Just wait.
Sir, please accept this memento on our behalf.
Yeah, thank you, and it's my honor to.
Yes, sir. The honor was ours. Thank you, sir.
And I'm extremely sorry for some initial part. There was some internet glitch from my side, so yeah. So please accept my apology.
It's okay, sir.
No problem, sir. It is a very nice lecture.
Thank you.
Thanks for delivering.